The work we're presenting is about the use of portable NMR in order to quantify mammographic density in breast tissue. The project involves a large group of close collaborators that includes physicists, cancer and cell biologists, clinical radiologists, and breast surgeons. Everyone in the MRI community is aware of the continuous push for higher and higher magnetic fields in MRI instrumentation. High B0 enables greater signal-to-noise ratio, which in turn allows radiologists to acquire images faster or with greater resolution than at a lower field. However, the work we are presenting follows a different paradigm. We're moving to lower fields and towards portable, inexpensive instrumentation in order to create the technology for mass routine screening of mammographic density. First of all, let's examine what mammographic density is and why it's significant. Empirically, mammographic density manifests itself as the degree of radioopacity of the breast on a two-dimensional X-ray mammogram, which is the standard imaging modality used for breast screening. A typical mammogram will have a mixture of radiodense and radiolucent areas. In radiodense areas, the absorption of X-rays is relatively high and these areas appear bright. In radiolucent areas, the absorption of X-rays is relatively low and these areas appear dark. Bright radiodense areas are known as areas of high mammographic density. Mammographic density is an individual characteristic and that is determined by a combination of genetic, biological, and physiological factors. Like all individual characteristics, there is a wide distribution of MD across the general population. Most women have MD within one standard deviation of the average, but a certain percentage have mammographic density that's either extremely high or extremely low. Biophysically, mammographic density is understood to represent the composition of the breast tissue, more specifically the relative fractions of adipose tissue and fibroglandular tissue. Breasts with low MD contain a relatively large proportion of adipose tissue, while breasts with high MD contain a relatively large amount of fibroglandular tissue. Mammographic density is clinically significant for two reasons. First, high mammographic density can act as a masking factor that makes it more difficult to detect abnormal features of the breast, such as cancer lesions. Therefore, an individual with an abnormally high MD would be at an elevated risk of a false negative result in a cancer screening test. Second, high MD is a significant cancer risk in its own right, irrespective of any issues related to diagnostic accuracy. Women in the highest quartile of mammographic density have the risk of developing breast cancer that is several times higher than those in the lowest MD quartile. In fact, MD is the highest, second highest independent risk factor for breast cancer after BRCA1 and BRCA2 genes. Therefore, women with high mammographic density have a dual reason to be extra vigilant towards breast cancer. X-ray-based mammography is the traditional clinical way of quantifying mammographic density. Computed tomography can also be used as a proper three-dimensional alternative. However, X-ray-based techniques are not always suitable. They're not recommended for young women or women recovering from surgery or women with certain inherited syndromes associated with radiosensitivity or cancer risk. Even in average patients, the maximum recommended mammogram frequency is once every 2 years. At the same time, there are clinical scenarios where it is advantageous to know the dynamic changes in mammographic density that occur on the time scale of weeks or months. Therefore, there has been a push to develop alternative techniques for measuring MD that do not involve ionizing radiation. In this work, we explored the versatility of magnetic resonance for tissue imaging, but we aim to avoid the high price tag associated with high-field MRI. We used commercially available portable NMR instrumentation, known as NMR mouse. It costs a very small fraction of high-field MRI scanners. It is based on an assembly of permanent magnets and requires no cryogens, therefore it also entails minimal maintenance costs. The permanent magnets are assembled such that they create a horizontal static magnetic field, whose strength can be between 0.3 and 0.5 Tesla, depending on the model. Furthermore, there is a very strong vertical magnetic field gradient with our particular instrument 22.5 Tesla per meter. This means that the signal is acquired from a very thin sensing slice of the order of 50 micron thick that hovers at a certain height above the magnets. The lateral size of the sensing slice is approximately the size of the surface coil that acts as both the transmitter and the detector coil. The assembly of magnets is mounted on a lift that is driven by a high-precision stepper motor, and this allows the sensing slice to be moved up or down, and thus the depth profile of the sample to be obtained. The work in this paper was carried out on slices of breast tissue from patients undergoing either prophylactic mastectomy or breast reduction surgery. A photograph of a representative slice is shown in the left picture. We acquired a slice mammogram for each slice measured. This is shown on the right, and a radiologist identified areas of high and low mammographic density in each slice. The magnetic resonance signal of fibroglandular tissue arises primarily from water, while the adipose tissue signal arises primarily from fat. As the first step, we measured the apparent T1 value for high mammographic density and low mammographic density regions in each slice. We then excised the respective high mammographic density and low mammographic density regions and measured the apparent T1 value in each of those regions again. Finally, the excised high and low mammographic density tissue samples were soaked in heavy water saline. This preserved the hydration of the tissue but displaced the protonated water, and therefore led to the loss of the water signal, while leaving the fat signal unchanged. This is a summary of our T1 results. In native tissue, both in the full slices and after excision, there is a statistically significant difference between the T1 values seen in HMD and LMD regions. After heavy water replacement, all samples showed approximately the same T1 values, which corresponded to the fat NMR signal. To summarize, the apparent T1 of breast tissue is sensitive to mammographic density, and we can differentiate between HMD and LMD region on the basis of the T1. The fact that HMD and LMD samples showed the same T1 values after heavy water exchange suggests that the microenvironment of the fat molecules is the same whether the fat is part of an HMD or an LMD region. The T1 of fat can therefore be used as a reference that potentially allows the fat-to-water ratio to be quantified. Portable NMR appears as a promising approach to the assessment of mammographic density without using ionizing radiation. More generally, we believe it could potentially become a new paradigm of biomedical imaging in applications where spatial localization rather than fine spatial resolution is required. We would like to acknowledge the people that who have contributed to this project, and thank you for listening.